Have you ever wondered why time seems to slow down when you're waiting for the bus, but speeds up when you're having fun? This is a question that has puzzled humanity for centuries. Time, as we know it, seems to be a subjective experience. It's elastic, it stretches and contracts based on our emotions, our activities, and our perceptions. But in the grand scheme of things, we all agree that an hour is 60 minutes, a minute is 60 seconds, and a day is 24 hours. Time, as we understand it, is a constant. In our everyday lives, we're governed by clocks, schedules, and routines. We plan our days around the relentless ticking of the second hand, the steady progression of hours on the clock face. Time is an immutable force, unyielding and inescapable. It marches on, indifferent to our pleas for it to slow down or speed up. Yet, what if I told you that time, in fact, isn't as rigid as we've come to believe? It's not a constant, but a variable, a dimension that can be manipulated and distorted. This isn't the stuff of science fiction, but the product of a revolutionary idea that transformed our understanding of the universe. In the early 20th century, a young physicist named Albert Einstein proposed a groundbreaking theory. He suggested that time and space aren't separate entities, but are intertwined in a four-dimensional continuum known as space-time. And most intriguingly, he suggested that time can be affected by motion and gravity. In essence, Einstein disrupted our conventional understanding of time. He presented us with a universe where time can stretch and squeeze, bend and warp. A universe where time, like a rubber band, can be stretched out and then snap back into place. So let's delve into the mystery of time. Let's explore the fascinating world of space-time, where the rules of physics as we know them seem to be turned on their head. What if I told you time isn't as constant as we think? What if it could stretch and squeeze just like a rubber band? Einstein challenged our understanding of time with his theory of relativity. Our perception of time and space was radically flipped on its head when a young physicist named Albert Einstein presented his theory of relativity in the early 20th century. Before Einstein, physicists like Isaac Newton viewed time and space as fixed entities, independent of each other. They were seen as a stage where events played out, but not actors in the play themselves. Enter Einstein, stage left, with a revolutionary idea. He proposed that space and time are not separate entities, but interwoven into a singular fabric he called space-time. Imagine a trampoline, where the fabric represents space-time. The presence of a heavy object on the trampoline creates a curve, just like a massive object like a star or a planet curves the space-time around it. Now here's the catch. According to Einstein's theory, the fabric of space-time is not just influenced by mass, but also by speed. The faster an object moves, the more space-time curves around it. This leads to some mind-bending consequences. One of these is the concept of time dilation. In essence, time dilation means that time does not tick at the same rate everywhere. A clock moving relative to an observer will tick slower than the observer's own clock. This is not because the moving clock is faulty, but because time itself is relative. It depends on your motion through space-time. Einstein's theory of relativity, with its intertwined space-time and its relative nature of time, was a radical departure from the established physics of the day. It challenged our understanding of the universe and continues to do so even today. It's the foundation of modern physics and has profound implications for everything from GPS technology to black holes. Einstein's theory of relativity suggests that time can be dilated. But what does that mean? That's what we're going to dive into next. So, brace yourselves as we embark on a voyage through time, exploring the strange and fascinating phenomenon of time dilation. Scene script. Time dilation sounds like something out of a sci-fi movie, but it's a real scientific concept. Let's simplify this mind-bending concept. Imagine two friends, let's call them Sam and Alex. Sam is on Earth, stationary, while Alex is on a spaceship zooming through space at near light speed. They both have identical clocks to keep track of time. From Sam's perspective on Earth, he sees his clock ticking away normally, second after second. But when he looks at Alex's clock aboard the spaceship, something strange happens. Alex's clock seems to be ticking more slowly. For every tick on Sam's clock, Alex's clock seems to take a bit longer to tick. Now let's switch perspectives. From Alex's viewpoint in the spaceship, his clock is ticking away normally, but when he looks at Sam's clock on Earth, it appears to be ticking faster. This apparent difference in the passage of time is what we call time dilation. It's not that the clocks are malfunctioning or that there's some optical illusion at play. It's that time itself is experienced differently depending on how fast you're moving or how much gravity you're experiencing. In essence, the faster you move, the slower time passes for you relative to a stationary observer. This isn't a result of perception, but a fundamental aspect of how our universe works, according to Einstein's theory of relativity. But you might say, wait a minute, if I'm on a fast train, I don't notice time slowing down. Well, you're right. The effects of time dilation are minuscule at the speeds we humans usually move. It's only at speeds close to the speed of light that time dilation becomes significant. So, according to Einstein, time can slow down. But how can we be sure that this is true? Scientists have conducted experiments to test the theory of time dilation. Let's dive into one of the most prominent examples, the Haferle-Keating experiment. In the early 1970s, two physicists, Joseph Haferle and Richard Keating, decided to put Einstein's theory to the test. They embarked on a journey around the world with 4 cesium beam atomic clocks, which are known for their incredibly precise timekeeping. 2 of these clocks were placed on commercial airliners, which flew twice around the world, once eastward and once westward. The other 2 clocks stayed at the United States Naval Observatory, serving as a stationary reference point. What happened next was mind-boggling. When the flying clocks returned and were compared to the stationary ones, they had indeed ticked at a different rate. The eastward traveling clock, moving against the rotation of the Earth, had lost time, while the westward traveling clock, moving with the rotation of the Earth, had gained time. The differences were minute, but they were there, and they matched Einstein's predictions. But it wasn't just the Haferle-Keating experiment that gave credence to time dilation. Other experiments, like those involving muons, particles that are produced when cosmic rays strike the Earth's atmosphere, also provided evidence. In their natural state, muons decay in a fraction of a second. However, when they're moving at near light speeds, they last much longer, as if time is stretching out for them. Again, just as Einstein predicted. So, it's not just about theoretical physics and chalkboards filled with equations. The reality of time dilation has been tested and observed in the real world through carefully crafted experiments conducted by curious and determined scientists. These experiments have shown that time dilation isn't just a theory, it's a reality. Time, that constant tick-tock we all live by, can stretch and shrink depending on how fast we're moving or how strong the gravitational field around us is. And that, my friends, is the beauty and mystery of time dilation. It's not just science fiction, it's science fact. So, what does time dilation mean for us in our daily lives? Well, even though we don't experience time dilation as dramatically as our hypothetical spaceship traveler, it does have real-world implications. For instance, consider the Global Positioning System, GPS, that helps us navigate. The satellites used for GPS are moving at high speeds and are far from the gravitational pull of the Earth. Both conditions that can cause time dilation. The clocks on these satellites tick faster than clocks on Earth, and even a tiny discrepancy can lead to huge positioning errors. To counter this, the system is designed with Einstein's theory of relativity in mind. The clocks are adjusted to account for the predicted time dilation, ensuring that your GPS can pinpoint your location accurately. While we might not notice it in our daily lives, time dilation is a fascinating concept that has far-reaching implications.